All right, everybody, welcome back. Today we're going to move into Unit 1, Section 5 of the AP Calculus course. We're going to talk today about determining limits using algebraic properties of limits. The properties that you see here today aren't, an exhaustive list of all the properties of different things that you can do algebraically with limits, but they are probably the most common ones you'll encounter and things that you might have to deal with, and they will be very helpful for us in doing some algebraic manipulation when we know the values of various limits and we look at algebraic combinations of those limits. So we've got one theorem here split into three parts that are going to introduce all the properties of limits that we'll use really in this course. So part A of our theorem, if we have a function that is a constant function, f of x equals k, then for any value of c, the limit as x approaches c of f of x is equal to the limit as x approaches c of k, which is equal to k. So if you think about it, if we pick any arbitrary value of c, let's say we pick c equals -4, and we think about what happens to this function as we get closer and closer to 4 from both sides, well, the y value is always going to be 6. And so here, no matter what our value of c is, I arbitrarily chose -4, but no matter what value of c we choose, the limit of that is going to be 6. Because as we get closer and closer to -4 from both sides, the value of the function is always 6. And so there's, the function stays on that same constant train throughout that entire section. All right, let's look at part B. If f is the identity function, f of x equals x, then for any value of c, the limit as x approaches c of f of x is equal to the limit as x approaches c of x, which is equal to c. So, suppose we arbitrarily approach 5, c equals 5. So we're talking about the limit as x approaches 5 of x here. And as x gets closer and closer to 5 from each direction, what happens with our y values, if you imagine walking up the curve in this direction and down the curve in this direction, they both get closer to a value of 5 as x gets closer to 5, since the y value on that function matches the x value on that function. Okay, so those two are pretty simple. The limit of any constant is that constant. The limit of the identity function is just the value wherever we're finding the limit. All right, part C is where we get into the meat of this. Theorem 1c, if L and M are real numbers, and L is the limit as x approaches c of f of x, and M is the limit as x approaches c of g of x, then we have various rules. We see rules here for the sum, difference, product, scalar multiple, quotient, and power. So if we take the limit as x approaches c of the sum of two functions, it's just equal to the sum of their two limits. That's what you see here. If you see the limit as x approaches c of the difference of two functions, that's just equal to the difference of their limits. That's what you see here. If you take the limit as x approaches c of the product of two functions, it's the product of their limits. If you take the limit as x approaches c of a constant times the function, that's equal to the constant times the limit of the function. If you see the limit as x approaches c of the quotient of two functions, it's the quotient of the limits as long as the one in the denominator is not equal to 0. And if you see the limit as x approaches c of a function raised to a power, that's equal to the limit raised to the power. Okay, so we can use all these properties for when we know the values of limits as x approaches a particular value to algebraically manipulate expressions that contain algebraic combinations of those functions. Let's go ahead, we'll work through example 1 here. Okay, first, limit as x approaches 3 of 2f of x plus 7. So the first thing I'm going to do is I'm going to use the sum rule, and I can break this into the limit as x goes to 3 of 2f of x plus the limit as x goes to 3 of 7. And then I can use the constant multiple rule, and I can bring the constant multiple 2 out of this limit, and this is going to be equal to 2 times the limit as x approaches 3 of f of x plus the limit as x approaches 3 of 7. And then I can go ahead and substitute. I know that the limit as x approaches 3 of f of x, which we see right here, that is equal to 2. So I can replace that with a 2. And from our very first part of our theorem, the limit as x goes to 3 of a constant is just the value of that constant. And so we end up with a limit here of 11 in part A. Now, as you do these problems, you'll realize that you don't necessarily need to show this exact detail in work that I did on this first one. I broke it up step by step. First I used the sum rule, then I used the constant multiple rule, and then I evaluated all of those limits. We can break it down a little more quickly than that to save ourselves some steps. For instance, in example B, I have a quotient. I'm going to break it up using the quotient rule, but then at the same time within that quotient I'm going to apply the other rules, the sum rule, the difference rule, the constant multiple rule, to save myself some writing. So this expression is going to be equal to the limit as x goes to 3 of f of x plus the limit as x goes to 3 of x all over 3 times the limit as x goes to 3 of g of x minus the limit as x goes to 3 of 2. And so we break it up that way, and now we can replace all of these things with what they are equal to. The limit as x goes to 3 we said earlier was 2. I'm going to use theorem 1 part B here for the right hand side of our numerator. Limit as x goes to 3 of the identity function, it's just going to be 3, is over 3 times the limit as x goes to 3 of g of x, which is negative 3, minus the limit as x goes to 3 of 2, which is just going to be 2, and then we go ahead and calculate all that, and we end up with negative 5/11 as our limit. Okay? And then we go to part C. The limit as x goes to 3 of the quantity 2f of x plus 4g of x to the 2/3 power. The limit of some expression raised to the n power is equal to the limit of that expression raised to the power. So this is going to be equal to the limit as x goes to 3 of 2f of x plus 4g of x, all raised to the 2/3. And then I can apply my properties inside that expression as well. And so this is going to be 2 limit as x goes to 3 of f of x plus 4 limit as x goes to 3 of g of x, all of that raised to the 2/3 power. I substitute values in here now. Limit as x goes to 3 of f of x was 2. Limit as x goes to 3 of g of x was negative 3. And so this all becomes 4 minus 12. That's negative 8 to the 2/3. And negative 8 to the 2/3, I take the root first. So that's negative 2, quantity squared. Negative 2 squared is positive 4. And so that's going to be the value of our limit. That's the end of example 1. And those of you who are taking this in my class, you'll see when you turn to the next page, we've got a couple of pages of practice with properties of limits, giving you some opportunities to apply some things you've learned in this lesson and some of the previous lessons. And then at the very end of that practice is a reminder that you have an assignment on my AP that's due before the next class. Okay, see you next time. Next time we're going to get into Unit 1, Section 6, determining limits using algebraic manipulation. I'll see you all then. Have a great rest of your day.